Okay, I think we are live. Yep. So last time we read chapter 10, section 2, traits. Was actually interesting topic. So basically traits, it kind of uh, interfaces in another languages. So yeah, we can use them as a type. We can use them with generics. We can have default implementation. Yeah, there is generics. We can bound the type of generics. We can use multiple trait bound. Trait bound with the clauses. Yeah, clear trait is, yeah, we can use alternative way to define the bounds instead of explicitly say in these angle brackets. We can use keyword where and explain it after return type. We can use return type as a trait as well. And etc. So today we are going to read chapter section 3, validating reference with lifetimes. Looks like a big section. Let me quickly check my layout. Yeah, I think it's good. So yeah, let's go on. So lifetime are another kind of generic that we are already been using. Rather than ensuring that type has behavior we want, lifetimes ensure that references are valid as long as we need them to be. So this is some mechanism that ensure that references are valid as long as we defined. One details we didn't discuss in the reference and borrowing section in chapter 4 is that every reference in Rust has a lifetime. Okay. Which is the scope for which that reference is valid. Most of time lifetimes are implicit and inferred. Just like most of the time types are inferred. We only must annotate types when multiple types are possible. Yeah. Like here it's I32, but if we want something else, U8, for example, we need explicitly specified. Okay, I lost the place. Okay, yeah, types are possible. In similar way, we must annotate lifetimes when the lifetimes of the reference could be related in a few different ways. Rust requires us to annotate the relationships using generic lifetime parameters to ensure the actual reference used at runtime will definitely be valid. Okay, so if we want to change default behavior of the lifetime, we need somehow specify it. Yeah. So annotating lifetime is not even a concept most other programming languages have. So this is going to feel unfamiliar. Okay. Also, we won't cover lifetimes in their entirety in this chapter. We discuss common ways you might encounter lifetime syntax, so you can get comfortable with the concept. Okay. So, preventing dangling references with lifetimes. The main aim of lifetimes is to prevent dangling references which cause the program to reference data other than the data it's intended to reference. Consider the program in list in 10.16, which has an outer scope and an inner scope. So what we have here? So we have this main outer scope and inner scope of X, and basically, yeah, of X, and in inner scope we're doing the reference. We assign R reference of inner scope, so it might cause an error. Let maybe start new project, cargo new lifetimes 10. So let X, and yeah, exactly, and we want to print R here, and we immediately, even without building, get an error. X does not live long enough. Borrow value does not live long enough. Exactly, as we expected. So the example in listing 10.16, 10.17, and 10.23 declare variable without giving them an initial value. So the variable name exists in outer scope. At first glance, this might appear to be in conflict with Rust having no values. However, if we try to use a variable before giving it a value, we'll get a compile time error, which shows that Rust indeed does not allow null values. Yeah, that's a good point. The outer scope declares a variable name R with no initial value, and the inner scope declares a variable named X with the initial value of 5. Inside the inner scope, we attempt to set the value of R as a reference to X. Then the inner scope ends and we attempt to print the value in R. Okay. This code won't compile because the value R is referred to has gone out of scope before we try to use it. Here is the error message. Borrowed value does not live long enough. X drop here was still borrowed. Okay. Yeah, this is kind of obvious and clear. Get enough knowledge to understand it already. Variable X doesn't live long enough. The reason is that X value be out of scope when the inner scope ends on line 7, but are still valid for the outer scope. Because its scope is larger, we say that it lives longer. If Rust allowed this code to work, R would be referencing memory that was deallocated when X went out of scope, and anything we try to do with R wouldn't work correctly. So how does Rust determine that this code is invalid? It uses a borrow checker. Oh, borrow checker. Sounds cool, borrow checker. So yeah, I think important concept. So the Rust compiler has a borrow checker that compares scopes to determine whether all borrows are valid. List in 1017 showed the same code as list in 1016, but with annotations showing the lifetimes of the variables. So basically the same, but yeah, you see this single quote appear here. It's something new. Let's find out. But yeah, basically show the scope here and scope here. Okay, here we annotated the lifetime of R with I don't know, is it semicolon? Sorry, not semicolon, single quote A, and the lifetime of X with single quote B. As you can see, the inner B block is much smaller than the outer A lifetime block. At compile time, Rust compared the size of the two lifetimes and sees that R has a lifetime of A, but that it refers to the memory with a lifetime of B. The moment is rejected because the program is rejected because B is shorter than A, and the subject of the reference doesn't live as long as a reference. Okay. Fixes the code so it doesn't have a dangling reference and compiles without any error. So we basically remove the curly brackets, so it's now in the same scope. Here's X has lifetime B, which in this case is larger than A. This means R can refer B. Okay. This means R can reference because Rust knows that the reference in R will always be valid while X is valid. Okay. Now that you know where the lifetimes of reference are and how Rust analyzes lifetimes to ensure references will always be valid, let's explore generic lifetimes of parameters and return values in the context of functions. So generic lifetimes in functions. We'll write a function that returns the longer of two string slices. This function will take two string slices and return a single string slice. After we implemented the longest function, the code in 1019 should print the largest string is ABCD. So have string 1, string 2, then we invoke largest as is char, and this is char. All right. So note that we want the function to take string slices, which are references, rather than strings, because we don't want the longest function to take ownership of its parameters. Refer to string slices as a parameters section in chapter 4 for more discussion about why the parameters we use in list 1019 are the ones we want. If we try to implement the longest function as shown in list 1020, it won't compile. So let's do this. And also copy this snippet. Missing lifetime specifier. Okay, so Rust analyzer catch it. Just try to build to make sure it's correct, because sometimes Rust analyzer, at least in NeoVim, it shows you something wrong and you need to restart LSP. But yeah, now it's the same error and it's expected. So instead we get following error that talks about lifetimes. Expected name lifetime parameter. This function return type contains a borrow value, but the signature does not say whether it is borrowed from X or Y. Help, consider introduce a named lifetime parameter. Okay. So I guess what we can do here, we can, it's just my prediction, but I think we can specify that the return string will have same lifetime as I don't know, as one of our params, or for example it will have lifetime of string 1 or something like this. Really interesting. The help text revealed that the return type needs a generic lifetime parameter on it because Rust can't tell whether the reference being returned referred to X or Y. Actually, we don't know either, because the if block in the body of this function return a reference to X and the else block return reference to Y. When defining this function, we don't know we can create values that will be passed into this function, so we don't know whether the if case or the else case will execute. We also don't know the concrete lifetime of the references that will be passed in, so we can't look at the scope as we did listing 1017 and 1018 to determine whether the reference we return will always be valid. Okay, the borrow checker can determine this either because it doesn't know how the lifetime of X and Y related to the lifetime of the return value. To fix this error, we'll add generic lifetime parameters that define the relationship between the references so the borrow checker can perform its analysis. So, lifetime annotation syntax. So how we can specify this lifetime parameter. Lifetime annotation doesn't change how long any of references live. Rather, they describe the relationship of the lifetimes of multiple references to each other without affecting the lifetimes. So, okay. Just as functions can accept any type when the signature specify a generic type parameter, functions can accept references with any lifetime by specifying a generic lifetime parameter. Okay. Lifetime annotation have a slightly unusual syntax. The name of lifetime parameter must start with an apostrophe. Okay, this is called an apostrophe. And usually all lowercase and very short. So usually basically mean it's not supposed to be, but it's something like unwritten rule. Like generic types. Most people use the name apostrophe A for the first lifetime annotation. We place lifetime parameter annotation after the reference. Ampersand of reference, using a space to separate the annotation from the references type. Here are some examples. A reference to an I32 without a lifetime parameter, a reference to an I32 that has lifetime parameter named apostrophe A, and mutable reference to an I32 that also has the lifetime apostrophe A. So a reference with an explicit lifetime, a mutable reference with explicit lifetime. Okay. Once lifetime annotation by itself doesn't have much meaning because the annotations are meant to tell Rust how generic lifetime parameter of multiple references relate to each other. Let's examine how the lifetime annotation relate to each other in the context of the longest function. Okay. Lifetime annotation in function signatures. To use lifetime annotation in function signature, we need to declare the generic lifetime parameters inside angle brackets between the function name and the parameter list, just as we did with generic type parameters. So like this, but with apostrophe. We want the signature to express the following constraint: the return reference will be valid as long as both parameters are valid. This is the relationship between lifetimes of the parameters and the return value. Let me read it again. We want the signature to express the following constraint: the return reference will be valid as long as both parameters are valid. So, okay. The return reference will valid as long as this reference and this reference will be valid. This is the relation between lifetime of the parameter and the return value. We'll name the lifetime A and then add it to each reference and show in listing 1021. So let me try to do this. So angle bracket apostrophe A, then we want apostrophe A, and I think it was something like this. So yeah, it works. So this, I see how the lifetime explanation is said that we don't change the lifetime, we just specify relations. So string 1 and string 2 lifetime is not changed. It works as it was, but it's explicitly specified to the longest function, so we return x or y, and yeah. But let's see what the explanation in the book. So this code should compile and produce the result we want when we use it with the main function in list in 1019. The function signature now tells us that for some lifetime apostrophe a, the function takes two parameters, both of which are string slices that live at least as long as lifetime a. The function signature also tells us that the string slice returned from the function will live as at least as long as lifetime a. In practice, it means that the lifetime of the reference returned by the longest function is the same as the smaller of the lifetimes of the values referred to by the function arguments. Those relations are what we want Rust to use when analyzing this code. Okay. Remember, when we specify the lifetime parameter in this function signature, we're not changing the lifetimes of any value passed in or returned. Rather, we are specifying that the borrow checker should reject any values that don't adhere to those constraints. Note that the longest function doesn't need to know exactly how long x and y will live, only that some scope can be substituted for a that will satisfy this signature. Yeah, exactly as I thought. So we're not changing it, we just tell that x and y will live as same as smaller time of each parameter, and return type will have same lifetime. Okay. When annotating lifetime in function, the annotation go in the function signature, not in the function body. Okay, this lifetime annotation become part of the contract of the function, much like the type in the signature. Having function signature contained in the lifetime contract means that analyzes the Rust compiler, thus can be simpler. Oh my gosh. If there any problem with the way a function is annotated or the way it's called, the compiler errors can point to the part of our code and the constraints more precisely. If instead the Rust compiler made more inferences about what we intended the relationship of the lifetime to be, the compiler might only be able to point to use of our code many steps away from the cause of the problem. Okay, yeah, so what I understand from here is that explicitly specifying our relationship of lifetimes is simplify the Rust compiler. It's not trying to predict and end up with not messing with what we're gonna do, because it obviously that language cannot exactly predict what we're trying to do. We can do mistakes and it will do assumption on our mistakes, etc. When we pass concrete reference to the longest, the concrete lifetime that is substitute for A is the part of the scope of X that overlaps with the scope of Y. In other words, in the generic lifetime A will get the concrete lifetime that is equal to smaller of the lifetimes of X and Y, because we have annotated the returned reference with the same lifetime parameter A. The returned reference will also be valid for the length of the smaller of the lifetimes of X and Y. Let's look at how the lifetime annotation restricts the longest function by passing in references that has different concrete lifetimes. Listing 1022 is a straightforward example. So we define string 1, then we create inner scope with string 2, then we use longest with string 1, string 2, and print the result. So it works, and if we move it out of we cannot move out it, right? Or if we specify a result. So yeah, let me just try to do it. I expect this will work. Okay, but what if we do let result yeah, just need semicolon, and this one is work as well. But what if we will try to print it outside? There is an error because the smallest lifetime is in string 2 and it will end up in this block, so it will be not valid anymore here. Okay, actually let's take a look what the error looks like. So borrowed value does not live long enough. Okay, yeah. In this example, string 1 is valid until the end of the outer scope. String 2 is valid until the end of the inner scope. And the result reference something that is valid until the end of the inner scope. Run this code and you'll see that the borrow checker approves. It will compile and print the longest string is exactly. Next, let's try an example that shows that lifetime of the reference in the result must be the smaller lifetime of the two arguments. We'll move the declaration of the result variable outside the inner scope, but leave the assignment of the value to the result variable inside the scope with string 2. Then we'll move the println the user's result outside the inner scope after the inner scope has ended. This code enlisted in 1023 will not compile. Yeah, exactly what we just tried. Because it just makes sense to try how it works. So yeah, this borrowed value does not live long enough. Exactly. So the error showed that for result to be valid for the println statement, string 2 would need to be valid until the end of the outer scope. Rust knows this because we annotated the lifetimes of the function parameter and return value using the same lifetime parameter a. As human, we can look at this code and see that string 1 is longer than string 2, and therefore result will contain a reference to string 1 because string 1 has not gone out of scope yet. A reference to string 1 will still be valid for the println statement. However, the compiler can't see the reference is valid in this case. We've told Rust that the lifetime of the reference returned by the longest function is the same as smaller of the lifetime of the references passed in. Therefore, the borrow checker disallowed the code in listing 1023 as possible having an invalid reference. Try designing more experiments that vary the values and lifetimes of the reference passed into the longest function and how the return reference is used. Make hypotheses about whether or not your experiments will pass the borrow checker before you compile. Then check to see if you're right. Yeah, good suggestion, but we will just move on. We did one experiment already. It was similar which one it was in the book. But anyway, thinking in terms of lifetimes. The way in which you need specify lifetimes parameter depends on what your function is doing. For example, if we change the implementation of the longest function to always return the first parameter rather than the longest string slice, we wouldn't need to specify lifetime on the y parameter. The following code will compile. And for sure, we'll try it out. So now there is no problem here, but we cannot return this one anymore. So we kind of can do this, I guess. Oh yeah, it's actually like it looks here. We've specified the lifetime parameter a for parameter x and the return type, but not for the parameter y, because the lifetime of y does not have any relationship with the lifetime of x or the return value. When returning a reference from a function, the lifetime parameter for the return type need to match the lifetime parameter for one of the parameters. If the reference returned does not refer to one of the parameters, it must refer to a value created within the function. However, this would be a dangling reference because the value will go out of scope at the end of function. Consider this attempted implementation of the largest function that won't compile. Okay, what we have here, lifetime same as returned value, but But yeah, it lifetime of returned value will end up with the scope, so it doesn't make any sense. Let's so can I return reference to local variable result, return a reference to a data owned by the current function. Yeah, so reference to result. So when we go out, it's not valid anymore. Here, even so, we've specified a lifetime parameter a for the return type. This implementation will fail to compile because the return value lifetime is not related to the lifetime of parameters at all. Here is the error message we get. Yeah, the problem is that result goes out of scope and gets cleaned up at the end of the largest function. We've also tried to return a reference to result from the function. There is no way we can specify lifetime parameters that would change the dangling reference, and Rust won't let us create a dangling reference. In this case, the best fix would be to return an owned data type rather than reference, so the calling function is then responsible for cleaning up the value. So is it say it better to do something like string and simply return? Can we do this? And it will actually work. Okay, so yeah, in this case I think we do move ownership from the function to the returned result, and result will take the ownership of this result string, and its lifetime will be in this scope. Okay. Ultimately, lifetime syntax is about connecting the lifetime of various parameters and return values of function once they're connected. Rust has enough information to allow memory safe operations and disallow operations that would create dangling pointers or otherwise valid memory safety. Okay. So lifetime annotation in struct definition. So far, the struct we've defined all hold owned types. We can define struct to hold references, but in this case, we would need to add a lifetime annotation on every reference in the struct definition. Listing 1024 has a struct name important excerpt that holds a string slice. Excerpt. Okay. So struct important excerpt, in angle bracket we have lifetime, and part has lifetime. of string. So we create novel string, first sentence. What the type? This actually string reference to string slice of novel. Then we create our important except struct, and put first sentence. So if we remove this, it will not work, right? Okay. So this struct has the single field part that holds a string slice, which is a reference. As with generic data types, we declare the name of the generic lifetime parameter inside angle brackets after the name of the struct, so we can use the lifetime parameter in the body of the struct definition. This annotation means an instance of important excerpt can't outlive the reference it holds in its part field. Okay. So if the first sentence lifetime ended, then the whole struct lifetime is ended as well, I guess. The main function creates an instance of the important except struct that holds a reference to first sentence of string owned by variable novel. The data in novel exists before the important except instance is created. In addition, novel doesn't go out of scope until after the important except goes out of scope. So the reference in the important except instance is valid. Okay. Lifetime elision. This is what is elision actually? The omission of sound or syllable when speaking. The process of joining together or merging in specifically abstract idea. Okay, so it's like merging of lifetimes, I guess. You learn that every reference has a lifetime and that you need to specify lifetime parameters for function or struct that use references. However, in chapter 4 we had a function in listing 49 shown again in listing 1025 that compiled without lifetime annotation. Let's take a look. So we receive in function string reference, string slice, return as well. Convert to bytes, and we return slice of the string. or the whole string. And here we don't need specify, but I guess it because in previous example we have two variables and it can contain different lifetimes for each parameter, and it's not kind of straightforward. But in this case we have only parameter and the only lifetimes it can take the same as this parameter and return value same. So I guess Rust doing automatically this operation. The reason this function compiles without lifetime annotation is historical. Oh, okay. In early versions pre 1.0 of Rust, this code wouldn't have compiled because every reference needed an explicit lifetime. At that time, the function signature would have been written like this. So yeah, same as we did for two params. After writing a lot of Rust code, the Rust team found that Rust programmers were entering the same lifetime annotation over and over in particular situations. Those situations were predictable and followed a few deterministic patterns. The developers programmed those patterns into the compiler's code so the borrow checker could infer the lifetime in this situation and wouldn't need explicit annotation. This piece of Rust history is relevant because it's possible that more deterministic pattern will emerge and be added to the compiler. In the future, even fewer lifetime annotation might be required. So yeah, I kind of guess why it's going on. And basically it means when you write code, first you write it without annotation, and if you have the errors, then you put the annotation, because maybe the annotation you written before is not needed anymore because of Rust update, some new version, new pattern were added. The patterns programmed into Rust analysis of references are called in lifetime elision rules. Okay, lifetime elision rules. Those aren't rules of programmers to follow. There are a set of particular cases that the compiler will consider, and if your code fit those cases, you don't need to write the lifetime explicitly. The elision rules don't provide full inference. If Rust deterministically applies the rules, but there is still ambiguity as to what lifetime the references have. Sorry. The elision rules don't provide full inference if Rust deterministically applies the rules, but there is still ambiguity as to what lifetimes a reference have. The compiler won't guess what the lifetime of the remaining reference should be. Instead of guessing, the compiler will give you an error that can resolve by adding the lifetime annotation. Yeah, exactly what I was thinking and how it works. Lifetimes on function or method parameter are called input lifetime. Input lifetimes, okay. And lifetimes on return value are called output lifetimes. Okay. The compiler uses three rules to figure out the lifetimes of the reference when there aren't explicit annotation. The first rule applies to input lifetimes, and the second and the third rules apply to output lifetimes. If the compiler gets to the end of the three rules and there are still references for which it can figure out lifetimes, the compiler will stop with an error. The rules apply to function definition as well as implementation blocks. The first rule is that the compiler assigns a lifetime parameter to each parameter that a reference. In other words, a function with one parameter gets one lifetime parameter. Okay. A function with two parameters gets two separate lifetime parameters. Okay. And so on. The second rule is that if there is exactly one input lifetime parameter, that lifetime is assigned to all output lifetime parameters. If there is exactly one input, that lifetime assigned to all output. Okay. So it can find out is the return is always 1. Lifetime, it assign it to output. The third rule is that if there are multiple input lifetime parameters but one of them is self or mod self, because this is a method, the lifetime of self is assigned to all output lifetime parameters. This third rule makes method much nicer to read and write because fewer symbols are necessary. Alright, let's pretend we are the compiler. We apply these rules to figure out the lifetime of the reference in the signature of first word function in list in 1025. The signature starts without any lifetime associated with the reference, so it's here. So we set each parameter, so we put angle brackets lifetime a here, lifetime a here, and we check if there is only one output, and this is also lifetime a. We put lifetime a here as well, and this is how I think it. So then the compiler applied the first rule, which specifies that each parameter gets its own lifetime. We call it a as usual. So now the signature is this. So yeah, first apply to each parameter. The second rule apply because there is an exactly one input lifetime. The second rule specified that the lifetime of the one input parameter gets assigned to the output lifetime. So the signature is now this. Now all the references in this function signature have lifetimes, and the compiler can continue its analysis without needing the programmer to annotate the lifetime in this function signature. Let's look at another example, this time using longest function that had no lifetimes parameter when we started working with it in list in 1020. So yeah, so to each parameter we assign a lifetime a and b. Let's apply the first rule. Each parameter gets its own lifetime. This time we have two parameters instead of one and have two lifetimes. Okay, but return value can be either a or b, so compiler can't automatically assign output value. You can see that second rule doesn't apply because there is more than one input in lifetimes. The third rule doesn't apply either because longest is a function rather than a method, so none of the parameters are self. After working through all three rules, we still haven't figured out what the return type lifetime is. This is why we got an error trying to compile the code in less than 1020. The compiler worked through the lifetime elision rules, but still couldn't figure out all the lifetimes of the references in the signature. Because the third rule really only applies in the method signature, we'll look at lifetimes in that context next to see why the third rule means we don't have to annotate lifetime in method signature very often. So lifetime annotation in method definition. Okay, so now let's take a look. When we implement method on struct with lifetimes, we use the same syntax as that of generic type parameters shown in list in 10.11. Where declare and use lifetime parameters depends on whether they related to the struct field or the method parameters and return values. Lifetime names for struct field always need to be declared after the implementation keyword and then used after the struct name, after the struct's name, because those lifetimes are part of the struct's type. In method signature, inside the implementation block, reference might be tied to the lifetime of reference in the struct field, or they might be independent. In addition, the lifetime elision rule often make it so that lifetime annotation aren't necessary in the method signature. Let's look at some example using the struct name important excerpt that we defined in list in 1024. First, we use the method named level, whose only parameter is reference to self and whose return value is ICT2, which is not reference to anything. Okay, let's add it. Nothing broken. Not return a reference here, but we get reference to self. The lifetime parameter declared after. Oh, we have lifetime parameters declared. Yeah, I missed this part. So after implementation, we put here and here. What will happen if we delete it? Implicit elided lifetime not allowed here, assuming a static lifetime. The lifetime parameter declaration after implementation in its use after the type name are required. But we're not required to annotate the lifetime of the reference to cell because of first elision rule. Here's an example where the third lifetime elision rule applies. Let's copy it. I think we can do it in this block. So we take cell, then we take another reference, and this third rule say it all take the self lifetime, I guess, or what? There are two input lifetimes, so Rust applied the first lifetime elision rule that gives both self and an announcement their own lifetime. Then, because one of the parameter is self, the return type gets the lifetime of self. Okay, and all lifetimes have been accounted for. Okay, so yeah, we have like lifetime A here, lifetime B here, and lifetime A here because it's lifetime of their self. So a static lifetime. Oh, it feels like endless section. It's again and again new and new terms here. One special lifetime we need to discuss is static. This denotes that the affected reference can live for the entire duration of the program. All string literals have the static lifetime, which we can annotate as following. Okay. So the lifetime as long as the program exists. Okay. The text of this string is stored directly in the program binary, which is always available. Okay. Therefore, the lifetime of all string literal is static. You might see suggestion to use the static lifetime in error message, but before specifying the static as a lifetime for a reference, think about whether the reference you have actually lived the entire lifetime of your program or not, and whether you want it to. Most of the lifetime and error message suggestion the static lifetime result from attempting to create a dangling reference or a mismatch of the available lifetimes. In such cases, the solution is fixing those problems, not specifying the static lifetime. So yeah, basically compiler can suggest us to use static to fix the problem, but we should make sure if we use static, it's something that we won't leave the whole program duration. If not, we should solve it in different way. So yeah. Generic type parameters, trait, bounds, and lifetime together. So this is kind of all three sections: generic data types, traits, and lifetime together. Let's briefly look at the syntax of specifying generic type parameters, trait, bounds, and lifetimes all in one function. Oh, let's do. So here we have the function specify lifetime, and then comma generic, then references with a lifetime, and return value is lifetime, where t bounds to the display. So basically t had to implement display trait and what is n? Oh, I see. And a sort parameter which is type t, which is implement trait display. That's why we can use it in println. And then the longest as we had before. This is the longest function from list in 1021 that returns the longest of two string slices. Sorry. This is the longest function from list in 1021 that returns the longest of two string slices, but now it has an extra parameter named and of generic type T, which can be filled in by any type that implements the display trait as specified by where clause. This extra parameter will be printed using curly brackets, which is why the display trait bound is necessary. Because lifetime are a type of generic, the declaration of the lifetime parameter A and the generic type parameter T go in the same list inside the angle brackets after the function name. Okay, so the summary of the chapter 10. We've covered a lot in this chapter, it's for sure. Now that you know about generic type parameters, traits and trait bounds, and generic lifetime parameters, you are ready to write code without repetition and that work in many different situations. Generic type parameters let you apply the code to different types. Trait and trait bounds ensure that even though the type are generic, they'll have the behavior the code needs. You learn how to use lifetime annotations to ensure that this flexible code won't have any dangling reference, and all this analysis happen at compile time, which doesn't affect runtime performance. Believe it or not, there is much more to learn on the topics we discussed in this chapter. Chapter 17 discussed trait objects, which are another way to use traits. There are also more complex scenarios involving lifetime annotation that you will only need in very advanced scenarios. For those, you should read the Rust reference. This book is complete. The book is primary reference to the Rust programming language. It provides three kinds of material. Chapter that informally describe each language construct and their use. Chapter that informally describe memory model, concurrency model, runtime service, linkage model, and debug facilities. Appendix chapter that provide international reference and language influence the design. Okay, definitely more advanced topic that we need now. But next, you'll learn how to write tests in Rust so you can make sure your code is working the way it should. Woohoo! Yeah, I'm kind of like writing tests, not doing too much regular, but yeah, I love this concept of writing tests. We'll back to it on the next stream, maybe. Yeah, let's do couple exercise with the Rustlings as we traditionally do after the reading. Okay. So now we in modules exercise. This is first exercise for modules, and let's start. So what is the error? Function makes sausage is private, so we can just add pop and it's done. So move on. Expect identifier found question mark. Okay, so you can bring module paths into scopes and provide new names for them with the use and s keyword. Okay, fix the use statement to make the code compile. Execute. Okay. So peer as what? Delicious snacks, fruit. So I think what we need to do there, we need fruit and veggie. Nope. Yeah, semicolons. I'm currently working on the TypeScript project that not use semicolons, so now I'm constantly forgetting to add them, but this is not our problem. Private constant import. Should we make it public somehow? No. Private constant import. Can I do like this? All right, so yeah, I don't remember actually how it works, but we have this, how it's called, sorry guys, just everything messed up in my head. So basically this is private until we make it public, so we should to say we won't use this as public, but do we need, if we will like fruits, here, can you do it like this? Private model. The fruits is private model. So if we do it like this, it will work. Okay, so we can keep privacy here for the fruits, but we still can introduce with use as and make it public. Yeah, this is nice. Let's move on. So you can use the use keyword to bring sorry, lost the place. You can use the use keyword to bring module paths from modules from anywhere, and especially from the Rust standard library into your scope. Brings system time and Unix epoch from the std time module. Bonus style points if you can do it with one line. So std what it was, std time, and I think we can do something like this. System time, and what else we need? Unix, yeah, of course, semicolon in the end. Yeah, this was simple one. Let's move on. So next is the hash map exercise. Okay. A basket of fruits in the form of hash map need to be defined. The key represents the name of the fruit and the value represent how many of that particular fruit is in the basket. You have to put at least 3 different types of fruits, e.g. apple, banana, mango, in the basket, and the total count of all the fruits should be at least 5. So and I don't actually remember how we create hash maps. So what we're gonna do? Trust docs hash map. So we can create hash map new. And now we can start insert. So basket insert peer seven peer. I love peers. And yeah, basically just copy paste and apple and just 3. And yeah, we are done. So next exercise. A basket of fruits in the form of a hash map is given. The key represents the name of the fruit and the value represents how many of that particular fruit in the basket. You have to put more than 11 fruits in the basket. 3 types of fruits: apple, mango, and lychee, or already given in the basket. You are not allowed to insert any more of these fruits. So, okay, we have an arm here with fruits. There is apple, mango, and lychee. So we can add banana and pineapple. And to do, put new fruits if not already present. Note that you are not allowed to put any type of fruit that already present. Let me check. Fruit basket, where we use it. Here's our basket from this function. We created and put. So we can do insert like this. So basically we need to check if do we have, yeah, basket. I don't know, my LSP doesn't work, so let's back to it. Contain key. Returns true if the map contains a value for the specific key. So contain key fruit apple. If not contain key fruit apple, basket, insert, fruit, how much we need? 11. We already, I think 2 will be enough, but we still should fail because we should check unnecessary mismatch types. Expected reference to fruit. So test given fruit are not modified, at least 5 types of fruit. Greater than 11 fruits. What it actually checks. Sorry. Why it's not greater? I just wonder. Fruits count. Oh, it's panicked. Sorry. So it panicked. Not modified. Yeah, because we need to check. And okay, now I don't remember how the Boolean operations is happening. Is it control flow less than 5? What if I want less than 5? And maybe I just write it. Get some suggestion from the compiler. So apple, mango, and lychee. So necessary. So first of all, it complains there is no need to have this piece. Let's remove it. Oh, I did a mistake. So on the line 44. Much this closing this opening brace. Why? So expected block. Is in basket. Oh, basically I'm doing something completely wrong. I can use match, for example. Match. This is fruit. So if we have fruit, pineapple, mm, basket, insert. Put new fruits if not already present. Note that you are not allowed to put any type of fruit that already present. Sorry, I might be too tired, so I need to check if the fruit is so basket is contain key, and key must be reference to a fruit. If it's not, there we just do right. Yeah, super simple. I don't know. It's late evening already, so let's try the last one and maybe finish the stream. So at least one score, one per line of soccer match is given. Each line is of the form team 1 name, team 1 2 name, team 1 goals, team 1 2 goals. Example, England France 4-2. You have to build a score table containing the name of the team, goals of the team scored, and goals the team conceded. One approach to build the score table is to use hash map. The solution is partially written to use a hash map completed path to the test. So we have team. What is R here? R is results. So get results. Okay, where it fails. Build scores, panicked assertion, left equal right. So build scores table. Build scores table. Okay, this is our function. To do populate scores table with details extracted from the current line. Keep in mind that goals scored by team 1 will be the number of goals conceded from team 2, and similar. Goals scored by team 2 will be number of goals conceded by team 1. Okay, it should be simple, but yeah, just a bit tired. But I want to finish and I resolve it before to finish. So we have a hash map. We just need insert it correctly. So team list of scores. You have to build a score table containing the name of the team. Goal the team scored. Goal the team conceded. Okay. Okay, let's just see what the error. Have case. And it should be England, France, Germany, Italy, etc. So we just need score, insert team 1, team 1 score. Let's just try what. Oh, okay, expected struct. Where? Oh, okay, struct team goal score. Oh, now I get it. So just need and team name will be team 1 name, then goal scored team 1 score, and goal conceded is team 2 score. Okay, a user mode wallet in one name. I don't know, can I just do stupid things like from so yeah, looks like it works. We just need now to do same for team 2. One test is still failed. Validate team score. 1. So should I calculate? So for England we should have like 6, no, 5, 4. So get key value. Turn the key value corresponding to the applied key. The supplied key may be any board form. Get key value. Maybe let's quickly check. Do we have hash maps? Yeah. What we did when we read hash maps. So we did insert. We use entry. Oh, there is also a hint. How can I use hint? No. Or use hint watch for hint. Hint. Use the entry or insert. Yeah. To enter the entry corresponding to each team in the score table. If there is already an entry for a given key, the value returned by entry can be updated based on the existing value. If there is already an how do we know if there is already an entry, or this is the question. Yeah, this is so scores entry. Then we do or insert. So now what entry return? Not entry, but or insert. Okay. Let me use force insert. Goal scored. Oh, I get it now. What the idea we do default value is 0. Then if we do like this, team score basically pilot stable team 1 plus equal team 2, and same for the team goal score plus equal team 2 score and team 2 goals concede plus equal team 1 score. Let's clean up a bit. So cannot borrow scores. I think we need to place here. And we are done. Yoo-hoo. Yeah. It's simple task, but just my brain is not working anymore. So thank you everybody who was watching. See you on the next stream.